Sorry about that. I'm a little late today. How's everybody? All right, I could not find this thing. I finally found it. All right. So today is going to be review, and also I'll answer any questions you have. Are there any questions you want me to go over or topics you want me to review?
Yeah, like, do we get into operator overloading?
Operator overloading? No, you do not have to know that.
And also, should we be familiar with like the when we're doing like classes, like the off like the see out part, like friend?
You don't have to know friend.
Okay.
Yeah. Heaps. I don't think it was like heap and stack on the exam page. I don't think so, right? Recursive back. Hey. Yes. Yes.
Okay.
Sorry. I was like a little late today. Sorry. What did he say? Yeah, sure. Is there like a particular question you want me to go over, or should I just go over recursive backtracking in general?
It was one of the ones in
Crack?
Yeah.
Okay. Sure. We did that 2 sections ago, but I can go over it one more time if you want.
Actually, like,
Uh-huh.
could you explain like when you use a for loop in recursive backtracking as opposed to like not using a for loop?
Sure. Okay.
I know that it's like use a for loop when you're going over something larger.
Mm-hmm.
I still don't know, like, I don't know like how, like, when I should like unchoose in a for loop.
Mm-hmm.
Yeah.
Okay. Sure. Let's see. So let's see, recursive backtracking. Let's see. So how about I quickly pull up the should I just pull up the solution to crack and then I can explain it, or do you want me to like just develop it on the board? Because I covered that 2 sections ago.
Okay.
Let's see. Give me 1 sec while I pull it up. 106B. So let's see. Sections or. All right. So let's see. Crack, right? All right, let's take a look at the solution, and then we can talk about why you want to use a for loop, okay? So the key idea to think about whether or not to use a for loop is to think about what your choices are and how your how you're branching in your decision tree. Okay, in this example, the idea is you want to be enumerating over all possible sequences of like a certain number of letter words, like 5-letter words. In which case, if we start with an empty string, what would our choices be at each step?
Like A.
Yeah, like the choice would be what letter to put next into our string, right? So notice in this example, order matters. So when order matters, remember, we want to look at all of our choices and we want to decide which one to put at each position. Right? So at the first position, we can choose A, B, C, and then all the way up to capital Z. So A, B, C, Z. Okay? All right. Let's see. So this is like our first layer, and then at each of these, we can decide what the next character should be in our password. So we can also choose A, B, all the way up to Z. So this would be AA, this would be AB, this would be AZ. Okay? Now, the idea of using it, whether or not to use a for loop is when you're trying to decide which choice to go, if you have many, many different choices, then the idea is you want to loop over all your choices. Because you could also write 52 recursive calls, like one on each. But then it's much easier to like if you just make a recursive, if you just made a recursive call and then you just loop over all of your choices. Okay. I was grading Boggle last night, and a lot of you used like 8 different recursive calls.
Yeah, I remember you said that you could. I guess like you could use a for loop, right?
Yeah.
Yeah. I remember you like mentioned something like that I do, but I could not remember like I didn't know how to do it, so I just like did it 8 times.
Okay, yeah, I'll explain it during IGs, but the thing is, when you have like more than 4 or 5 recursive calls, it's you want to try to figure out a way so that you can go through all your choices without writing a recursive call for every single one of them.
Yeah.
Yeah. So like in this example, there's an easy way to loop over all of them. Just use a character and just loop over from A to Z. Okay. All right. Yeah. So you would use a for loop when you want to use a for loop in your choosing and unchoosing step when you have so many choices that it's not feasible to write a recursive call for each. Okay. Yeah. So this is like I mentioned 2 weeks ago there are 2 kinds of like recursive problems, and this kind of issue, this is not directly related to that difference, but let me quickly talk about that difference, because that difference often results in like a different amount of recursive calls. So you'll have these things called combination questions where order does not matter. So the order in which you make your choices don't matter. Right? Can you think of an example of a problem you've done where choices do not matter?
The one you were mentioning a few weeks ago with like how many weights.
Yeah. Right. I think it's like is measurable. Yeah. So for is measurable, remember that question was you had a bunch of like weights, and then you wanted to make sure like they balance each other, right? In this example, what were your choices at each step?
Either add the weight, subtract the weight, or don't do anything to the weight.
Right, yeah, which corresponds to adding to the left, right, or not doing it, right? Yeah. So notice because order does not matter, we are instead looking at our list of choices, and we're saying, okay, we're looking at our list of weights, and we're saying our choice is either take one of these. Our choices are a left, right, or neither. Okay. So in this example, order does not matter. In which case, our decision tree looks like we look at each one and we're saying left, right, or does not matter. That's different from this example in that this example, we're not looking at A to Z, and we're not saying, okay, this is A, this is B, this is C, and we're saying, okay, do I include or exclude A? Right? We're not doing that, because the thing is, if you do that, then you'll get a lot of like repeats. Well, not actually repeats. If you do that, you won't get all the choices because order does matter in this case, right? The order in which you choose the A's and the B's and the C's, it does matter. So in that case, because order matters here, what we do instead is we look at each position and we're saying, okay, what to put at each position. Position 1, do we put A, B, or C? Position 2, do we put A, B, or C?
So what would this type of recursive backtracking be called?
Oh, I just call it the permutations. Order does matter.
Oh.
Okay, so I just quickly draw how the recursive trees differ. If order does matter, then your recursive tree looks like what do I put in position X? Okay, this is permutation. So you would ask, like, you have positions. You have positions 1, 2, 3, 4. Actually, I should probably 0 index it. And then you'd ask, your choice is, what do I put at position X? Position 0, I'm going to put B. Position 1, I'm going to put Z. Right? That is different from position 0, I'm going to put Z. Position 1, I'm going to put B. Right, so in this case, your choose, when you want to choose to make the recursive call, when you want to choose to make the recursive call, you would essentially select which one to put at position 0, then which one to put at position 1. On the other side, if you wanted to do a combination problem, like let's see, it would be is measurable. Your choice is not, like, we aren't doing, okay, there are like 5 positions here, 5 positions here. Which one do I put at position 1? We're not doing that because that will cause the repeats. Instead, we're doing, look at each of these individually, one at a time. Look at this one. Where do you put it? We're not doing that over here. We're not saying, okay, A, where do I put it? We're saying, look at the position, which one to choose. Okay? It's the major difference between does the order matter or does it not matter. If the order does matter, then you are looking at each position and you're thinking which one to put in that position. And here, we're looking at each one and we're saying, where do I put that one?
Okay. So for the example that Julie did in class with like the states.
The what?
Like the state codes and like making words out of the states. I know like she used a for loop.
Let's see, the state and the codes.
It's like California's like CA, Alabama's AL.
Oh, I
and
see.
then,
Okay.
Like, she made like words out of them.
Yeah,
and,
yeah.
She like looked for the longest word, or just like the first word that was created, like the first word, and just stopped at the first word that was like created.
Sure.
Could you possibly like go over that code?
Yeah, sure. Okay,
Like,
so
yeah.
let's think about, suppose we had a list of states. C, A, L, and B. Okay, and then our choices, you can think of those choices. It's the same as like the one of these or one of these, right? It's a list of things that we want to put into, form our solution. Now, does the order in which I put them into my solution matter?
Yes.
It matters, right? Because we want to be able to like chain them so that the letters follow one after the other. So we have to put them in a certain order so that we know like which one goes after each other,
So
right?
it would be like a similar loop to crack, except we're just going through states instead of letters of the alphabet.
Now, I don't want to, don't think the for loop, don't think like the similarity between these two is the for loop. Okay, the similarity between these two is not the for loop. It's the fact that both of these are permutation questions. So what we're doing is we're saying, okay, we have position 0, position 1, position 2. Okay, and then we're saying, okay, position 0, which one do I put in there? Suppose I chose CA. Right. So that is our first recursive call. Our first recursive branch is, which one do I put in position 0? You can choose any of them, right? Then in position 1, we look at the ones that start with an A, because we put like a CA here. So we go through all the ones that start with an A. What other states start with an A?
Arizona, AZ.
AZ, okay. So then here we can choose either to put AL or AZ or some other ones. Right? Our recursive tree looks like in the first layer we can choose anyone. In the second one, or in the first index, we can choose to put anything that starts with an A. and then the second index would be all the states that start with whatever letter we ended with. Because order matters here, we're looking at each position one at a time, and we're saying which one to put there. Okay? But, so that is this example. We're looking at each of the choices, and we're deciding which one to put at each index.
She also used like the function, or like the method like get like contains prefix or prefix. Could you explain that?
Yeah, sure.
Yeah.
Okay, but before I get to that, let me finish one more thing here,
Okay.
which is let's see, yeah, the difference about the for loop. So the similarity between these two questions is not that they both use a for loop. It's that they're both permutation questions.
Yeah.
But oftentimes you'll see that permutation questions, you'll often be using a for loop here.
Don't often use it?
You will usually use a for loop.
Okay.
Yeah. Can you see why you would use a for loop in this example, not this example?
There's so many more choices.
Yeah, exactly. Because in the permutation question, you're looking at each index and you're thinking, which one do I put in the next index? You have to like go through all of these and try all of these, right?
Yeah.
But oftentimes in the combination problem, you're saying, okay, look at number one. Your choices are, do I put it on the left, right, or neither? You don't have a whole list of choices.
Yeah.
Now there are some problems where there's many different things you can do with the one. I think we can go over an example. You haven't done the make change problem, right? Make change? Okay, I'll quickly go over that question. It's a really good combination question. And then in that example, even though you're looking at one at a time, there are like so many different things you can do with it, you would use a for loop there. Okay?
Which one's the make change?
Yes, question.
Yeah, so if we're looping, let's say we need to loop, but we can't, like without duplication. So for example, if we picked A, we can't pick A again. In that case, then is it necessary to make some parameter that we have to pass in every call just to record, what we've already taken or what we've already used?
Yeah. If you can't duplicate, then you oftentimes you'll like in this example, because it's easy to loop through A to Z, so you don't have anything to store your choices. Oftentimes in the problem, you'll have like a list of things you can put as your choices, right? Let me just quickly draw one more thing. Oftentimes you'll have. Oftentimes you'll have something like bool. Let's see. This problem's called crack. Recursive. Right. Oftentimes you'll have like the thing you're building up. Let's not use crack. Let's use just some general recursive problem. Backtracking. Backtrack. Many times you'll have often like a vector or something, maybe a string, of things that you've chosen. So this corresponds to this, like things you've chosen. And then each one is the index. And then you also have a list of choices. Which corresponds to this thing. This is chosen. This is choices. Okay?
So with choices, would you like, if you choose it, you take it out of the vector?
Yeah, exactly. So you take it out and then make the recursive call.
And then you put it back in.
Yeah, exactly. The unchoose step would be you add it back in.
Okay. So
Okay.
when you add it back in, do you add it after the for loop?
Yeah,
Outside the for loop?
that's a good question. I'll give you a pretty good general rule of thumb, okay? Your unchoose step should be symmetric. Should be code-wise symmetric to the your choose step. Okay. So for example, let me think. Let me pull up the solution, and then you can see what I mean by symmetric. Yeah. So oftentimes there will be like different parts to your choosing and unchoosing. Different part that's like. Oftentimes you'll have to choose and unchoose different things. For example, if you have both a chosen vector and a choices vector, you have to add your choice to the chosen and remove it from choices. Right? So there's two things you have to do to choose. And your unchoose, you have to reverse both of them.
Yeah.
Okay. So for example, if you look at this question, Okay, this is not a great example to look at the choosing and unchoosing, but what would the choosing step be here?
Choose is when you're selecting the character.
Yeah.
The character that you're gonna add to
Yeah.
so far.
So here, so far plus C, what that does is it's making this choice of which one to put, right? And then when it's being passed into when it's passed to the recursive call, then you can see when it's passed to the recursive call, then you know that that like you've done choosing. This is the choose and the explore. There's no explicit unchoose step. Can you see why?
It just happens because you're not passing by reference.
Yeah.
Once you leave the call, you just go back up where so far is still so far.
Yeah. So yeah, you have to unchoose if you permanently changed some variable.
So far.
Yeah, because you never actually changed so far. You're just
Modifying it.
yeah, you're just making it like a temporary thing and just passing it in. Okay.
Okay.
Yeah. So this is not a good example, but if we looked at some other ones, let's see. It is measurable. See, like oftentimes we try to like do something like this. We just change it in the parameter so that we don't have to unchoose. A good example of oh wow, none of these are good. Here. Okay. So here you'll see you have the explicit choose, right? Okay. So yeah. So how I like to think about this is the choose. Notice that you also have a couple other chooses here, right? You're also subtracting from n.
Yeah.
Right? A choose is anything that modifies any of the parameters. So if here we modify the vector, and then we also make the value of n smaller. Yes.
The print squares one was really hard.
The print squares. Should I go over that one?
Yeah.
Okay.
It's not that like the code was difficult to understand. It was more of like setting it up was really difficult because like I don't know how to like because you have to think of it like mathematically before you make it into like code, and I don't like struggle with that.
Sure. Yeah. But let's quickly go over the intuition. Let's just like draw the tree, look at the intuition. Okay. But then like the way to think about let me quickly finish the thing about the symmetric unchoose and unchoose. Notice like I like to think of it like this. My for loop begins with an open parentheses, then I do the choose. So it means I have to unchoose before I leave this for loop. Okay.
Is the unchoose usually right before you leave the for loop, or like could you do like things after the unchoose?
Make them symmetric across the recursive call. So if you add inside the for loop, then unchoose inside the for loop as well. Okay, I like to think of it about it this way. You do all the choosings, make the recursive call, and then you unchoose in reverse order.
Okay.
So, for example, I like to put like this. So, choose one. Oh, let's say we have. Suppose we had a choose one here. Then we had an if statement. Then we had a choose two. Then we had a for loop. Then we had a choose three. And then recursive call. Okay.
Unchoose 3.
Yeah, so you'd unchoose 3 here.
And then unchoose 2.
Right?
And then
Unchoose
get out of
2.
the statement and then unchoose 1.
Yep. And then unchoose 1. Okay? Symmetric across each of them. The one thing to worry about is if you have like if you sometimes have this thing, if recursive call, then you return true, right? Sometimes the problem will state at the end of the function, you have to remember to restore everything, in which case, before you return, you should unchoose. Unchoose everything. Unchoose everything that is necessary. So unchoose everything, and then return true.
Okay.
Okay, and then you also have to explicitly unchoose here if it did not pass through that one. Okay? Yeah, the reason is because if you return true, then you skip all these unchooses. So you have to also like explicitly unchoose everything here. Okay? Yeah, you might not have to do everything.
Okay.
Okay, like for example, if you had like a chosen vector and a choices vector, because if the recursive call returned true, that means you found an answer.
Yeah.
In that case, you would not. That means you found an answer. You just want to return that answer to the user.
Yeah.
So you would not unchoose chosen.
Mm-hmm.
But sometimes the problem will ask you to like put everything back into choices. Don't like destroy choices. Yeah, if that's the case, then you want to put choices back in.
But just keep chosen.
Yeah, because chosen is the thing that you want to return to the user. Yeah, if you unchoose chosen, what happens is then your answer is always going to be empty.
Yeah.
Yeah.
There's another thing that just like syntactically.
Sure.
Sometimes like when I don't know when this happened, but like I think like Marty was doing it, but basically like you write something and at the end like you initialize like I don't know how to show it. Like it'd say like you did like print or just like do this thing, right? And then parentheses and these are the parameters. It was like int length or whatever and then comma string string word equals like the two little things.
Default parameters.
Yeah, what does that do?
So you won't have to do that for the exam.
Okay.
But a default parameter, what it does is if you don't pass in a parameter,
It's okay.
if you don't yeah, so that parameter you don't. It's like optional. If you
Oh.
don't pass it in, then
Yeah.
C++ just assumes that that was the parameter you wanted to put.
Oh.
Yeah, it has to come at your end. It has to come at the end of the parameter, all your parameters.
Wait, what?
It has to come at the end.
Oh,
Yeah.
okay.
So if you have like 3 parameters and an optional 4th one, then I can still call with 3 different parameters.
Okay. What if you had 2 optional parameters? They just both have to be at the end.
Both at the end. Yeah.
Okay.
Yeah. And then you have to you have to put them in the order in which like you'll need to call them. So if you want, like you're not allowed to say, okay, I want to put my own parameter 1, 2, 3, and 5, and I want to use the optional 4th one. You can't do that.
Okay.
Yeah, because if you think about it, then how do you skip the 4th parameter, right?
Yeah.
Yeah.
Also.
Let me answer his question
Yeah,
first.
sorry.
Okay. Yeah. Question.
So like just after like the question, could we just look at the so from midterm the practice midterm 1 the ring buffer queue reverse problem?
Okay. Sure.
Just after like we have a simpler.
Okay. Sure. Sure. Okay. We can go over that question. How about we go in order print squares, then we can look at that question. Okay. Can I go over print squares? Do you have another question?
Yes. Oh, when you initialize like ints and strings, like when you initialize like int or double, like do you have to say like int blah equals 0, or can you just do like int blah?
Is this for the classes question, or just in general?
In general, even
In
for
general?
classes too.
Okay. Yeah. So in general, like you can always initialize. You can always declare a variable by saying int I.
Yeah.
But the thing is, you can't use it. Well, you shouldn't use it until you set it to something. Okay, so if you have like a int main, right? You can always say int I. But then you shouldn't try to do something like cout I. Like you shouldn't try to do this
Okay.
because I could be anything.
Okay.
Yeah, so by good, like as a good habit, you should always initialize into like 0 or something.
Okay.
Okay.
Then with strings, you have to do the same thing with like.
So, yeah, strings are a little different because they are objects. Yeah. So remember, when you create an object, what happens when you create an object?
There's like a constructor with
Yeah.
some default parameters.
Yeah, yeah. So remember when you create an object, like when you create a vector or something, it calls that class's constructor.
Yeah.
So usually that constructor will do everything, like the initialization for you.
Okay.
Okay. Yeah. Okay. In the classes question, like you often have classes. Let's see. Let me write the classes example. In the classes example, where you have public. Let's see, class. So I don't exactly remember what the syntax is, but make sure you do. You have like 2 sections. It's a public section and a private section. You can put your instance variable in the private section. So suppose I had int size, and let's say we were storing like a dictionary, so a map of strings to ints. Okay. Then when we are writing our constructor, this is the .h file. This is the .cpp file. For the constructor, Do you remember what the syntax is to make to the constructor?
It's like, I
Mhm.
guess like whatever, maybe like void, right? Or
I think constructors don't have a return value, right?
oh, okay, and like class.
Yeah,
And
class.
then the colons, class.
Yeah. Okay, let's just say we put some parameter int size. Which reminds me, by naming convention, we start these with an underscore. Okay. All right. So and then when you declare some an object of the class, you would say you can pass in a parameter here, and then we can what would you do in your constructor?
I guess you make like the underscored size equals size.
Yeah. You would initialize all these with some of these, right? So you would say size is equal to size. Okay. Now you don't have to initialize dictionary.
Okay.
Why is that?
Because it's already the constructor for math is already doing that.
Yeah,
Okay.
because yeah, exactly. Because for objects,
The constructor does it.
right? When for objects, it already calls the constructors for these, so you don't have to initialize them explicitly.
Okay.
Okay. Yeah, that's it. Let's quickly go over print squares.
I think like when I wish that we could like bring some papers so that I could remember like more clearly like how things are written. You know, like just like yeah.
Yeah.
But it's also in the textbook, right?
Yeah, they're all in the textbook. I'd warn you about going through the textbook. Like you can definitely look it up when you are unsure about something, but I'd say Marty and Julie's exams are a time crunch, so don't waste too much time looking through the textbook. I think you'll get more points just by like going through the entire exam. Yeah,
Okay.
don't leave anything blank.
Okay.
Okay, like on the written questions, you get 1 point for writing the correct header.
Oh.
Yeah, so like please get that point.
Okay.
Oftentimes, like a third of the students miss that point
Oh.
because, and the reason why they miss the point is because they either the problem will always tell you what the parameters are, and then the student just forgets a parameter, or the most common issue they forgot to put an ampersand. Okay, when the problem says the parameters are a reference to an integer, make sure you say int ampersand. If it just says passes in a stack, make sure you don't put the ampersand.
Okay.
Okay, yes, question.
Just a question. So, like, let's say they have some parameters, but we want to add another one. Can we add that in as a parameter with a default value?
No, you may not change the function header itself.
Unless
Okay.
you make a helper.
Yeah, you can create a helper function.
Yeah.
Yeah, but you cannot like change that thing. Yeah, and also don't use default parameters on the exam because oftentimes that will that usually causes you more issues than necessary. If you want to, you can use you can overload the function. Do you know what that means? So you can declare the same name with like 2 different times. Yeah, with different parameters. If you don't know what that means, that's totally fine. But avoid using default parameters because it's like on your assignments, it's also really confusing if you use default parameters. People don't really use it too much. In C++, it's not being used too much anymore. Also because it's just kind of confusing. And then on the exam, just to make it's really easy to confuse yourself. Like you're like you misuse what the default parameter is, so it's kind of confusing. Okay, yeah, yeah. Just always use a helper function if necessary. Okay, let's go over print squares. Yeah. So the idea is we start with a number 200, and you want to decide what we want to find a sum of squares to add up to that number, right? Okay. So what is our list of what choices can we make at this step?
Start at 1.
So we can choose 1 squared, in which case we have 199.
Yeah.
Other choices?
2 squared.
2 squared. Okay. So that goes to 196, and you can go all the way up to 14 squared, and you have 4 left, right?
Sure, where can I find this problem?
This question's on the section handout for week 4.
3.
Yeah. All right. So this is our list of choices, right? We can go from 1 to 14. Okay. Now notice, suppose I chose 2. What choices do I have at this step?
You can 2, we can do 1 squared.
Yeah. So are we allowed to do 1 squared here?
Yeah.
Because the reason why we actually can't in this example because two things. One is it causes some repetitions.
Oh, because 1 squared already did that.
Yeah.
Oh,
Yeah.
okay.
Yeah. Because remember the thing that we print out at the end,
Mhm.
the squares have to be in increasing order,
Mhm.
right?
Yeah.
So once you've written 2 squared, you can't go back to 1
You
squared.
can do 3 squared.
3 squared, yeah. So you can go 3 squared.
So you can't repeat. You can't do like 2 squared.
I think you can repeat. Double check the question. Depending on what the question explicitly says.
It says unique positive integers.
Okay, yeah. So then you're not allowed to
Yeah.
repeat.
Okay.
In which case you just start from 3 squared.
Okay.
Okay. And then every time you have because of that, you get 187. Because you're not allowed to repeat. Think about this. This function call has no idea what numbers it can't use.
Yeah.
Right? Like, how do you know that at this step you're not allowed to use a 3 or a 2 or a 1?
You have
You-
to pass them, I think.
Yeah. So if you just think about that function call, it doesn't know what minimum it has. Then you have to think, oh, I probably need to pass some sort of parameter in there, right? I probably have to pass some sort of min value, right? So here, our min is 0 because we don't have any restrictions. But when we make this function call, what should our min be?
1, 2.
Depends on how you want to define min.
Oh, it's like 4, right? Or 9.
Yeah, or just I say there's many ways you can do it. I'll just put 3 here, which means you have to start at 3.
Okay.
Yeah, or 4, all the way up to 14.
Okay.
Okay. Here our min would be like 1. So here our min would be 2. The rule is just you can't go backwards.
Okay.
Okay. Yeah. So that's the intuition for why we need to pass this extra parameter.
Yeah.
Because otherwise, standing here, we have no idea that we can't go to 1. Right? We might just think, oh, 196. We can just start with 1.
Okay.
Okay.
We also do like a different branch, so we start off at 1, add 1 square, yes or no, and then next one, add 2 square, yes or no. So just kind of have everything like that. Will that work? Because this is unique.
Yeah, that would work because So oh wow, this is a really cool question because you can do it both as a permutation or a combination. Let's see. I think that also works. Let's write that tree out. You can also put this as a combination question where you're saying, right here, what we're doing is we're saying, okay, we have 1, 2, all the way up to 14, and we want to see these are our choices. I shouldn't draw them like that. Our choices are 1, 2, all the way up to 14. We're deciding in what slots to put them, right? We're saying, okay, which one to put in this slot. But we're specifically doing it so that once we put the 2, we remove this choice going forward. We're treating this as a permutation question, which works. This might actually be easier, where instead of treating these, treating this as a permutation question, where we're saying which one to put in the next index, we instead say, okay, let's look at the choices like this. 1, 2 to 14. And then we have a bag over here. We go through each one and we decide whether or not to put that into our choices over here. So we can go through 1 and we can decide, do we include 1 or exclude 1? So you can say include, exclude. 199, 200. Right, so we can decide whether or not to put 1 in here. Then we can think about 2. Right, shall we include or exclude 2? Um, 5, 99, include, exclude. Okay, and so on. Notice how these recursive structures are different, right? This one is we choose which one to go in the first position. After we do that, we remove all the ones that are smaller than that going forwards. Here, we're instead looking at each one individually and thinking whether or not they go in here. Yeah, so we don't have to worry about the min here because you know that you're going in order. So
Like it's just going back afterwards.
yeah,
Yeah.
at the end you'll get a list of increasing number of choices. You get like 1, 5,
Oh,
7, 10,
okay.
or something, right? Yeah. So you don't have to worry about order here. Okay. Yeah. Yeah. This is also a great way to look at the question.
This one, it's like if it's easier to understand this way.
Yeah, it is. So I'll just look at the question and think, does order matter? Even if order does kind of matter, notice that in this question,
How would you
Mhm.
make it so that you don't have to pass in like which number you're at? Or, like how does it know which number to keep track of? Like whether to include one or exclude one or two? Like how do you know whether to do one or two?
So that's something you have to pass as a parameter, right? What you could do is you could put this as a vector, and then every time just look at the first one.
Oh, and
So
then-
in every recursive call, you look at the first one and you decide whether or not to put it into your bag.
oh,
You're
okay.
chosen. This is choices.
So the vector, like after each call, I guess, like if you choose to, and like at the first one, would you just like delete the ones at the front? Or
Yeah,
something, like, take
yeah.
them out?
Yeah. So you look at like the first one and decide whether to include or exclude. Yeah.
So if you decide to include it, then you take it out of the vector.
Either way, you take it out of the vector because this is our list of choices.
Yes.
Once you've made a choice about whether or not to put one, you remove one. You put it or you don't put it, depending on whether or not you choose it,
Okay.
and then you make the recursive call so that
Okay.
it now looks at 2. Next.
Okay.
Okay.
Oh, okay. Okay.
Okay. What if I quickly change this question? Suppose repeats were allowed.
Repeats are allowed. Then you don't remove the
We'd have
choice.
to go to the. We couldn't use this method on the right because here we look at one, decide to include it or include it, but you could make that decision multiple times, right? So you'd have to. So on each one, you have to say, okay, from 1 to 14, what do I add? And then from there.
Okay. One thing you want to be careful of is that will cause repeats.
The right method? That's the one on the right?
There is a way we can make this work, okay? If you wanted to allow repeats here, it's pretty straightforward. Just instead of min equals 3, set that to min equals 2. Because that will allow 2 to be used again, right? Yeah, and then you can still ensure that it's going in increasing order. Once you go up to 3, you won't go back to 1 again. But then each time once you've chosen it, you just don't increment the min. You can just make it stay at 1 or 2. Make it the same as the choice you made. That will allow repeats here, right? That will allow repeated numbers.
Okay.
My concern here is if instead what you do is you don't remove 1. Notice that then it is possible to get like 1, 2 versus 2, 1.
Oh, okay.
Yeah, okay? So the way to do this is you still look at, in this idea, you're still looking at each one and you're deciding, do I exclude or do I include? Right? You still look at each one of these, but instead of include and exclude,
Stay the same? Like, don't do anything?
don't do anything is just the same as
Not including.
including it, right?
Add it 10 times?
Yeah. You can look at one element at a time. You're thinking, how many elements do I add? I can add 1 once, twice, 3 times. But then after this after I made my choice, I remove this. So if we were to redraw the recursive tree, it would look like.
Okay.
We redraw the recursive tree, that it looks like 200. We can include 1 ones, 2 ones, 3 ones, all the way up to 200 ones. Or we can also exclude.
2.
Right?
So,
0.
Oh, okay.
Making 200 different calls.
You're right.
There's so
once.
many.
This doesn't seem, I don't know if it's worse than the other one, but it just seems like you're making 200 calls just for 1 squared. And then you make another 200 to decide 2 squared.
So, how would you.
Yeah.
But I think it's
code?
So for this, you have to loop through them, right? You'd have to loop from 0 all the way up to 200 divided by 1. Right? In the second one, you'd have like 100 calls each.
Oh,
No,
yeah,
not
yeah. So it's
50
better.
calls each, and most 50 calls each, because each one can only go up to 50. Right? Yeah, these are actually similarly efficient. This one will also take as many recursive calls as that one because this one I mean. Because in this example, your min doesn't increase, so you could be stuck at 2 for a long time. You could just say, oh, add 2, add 2, add 2, add 2. Okay? So you can think about this. This has more layers because there's so many ways to get to 2. But this has just one layer of 2s. So this one is like not as deep. This one goes really deep.
Yeah.
Okay?
Okay.
Okay, they're both similar.
It's wide. This one's wide.
Yeah, this one's like really wide
Yeah,
and
that
it doesn't
one's-
go as many layers. Yeah, this will only go up to like level 14 or something,
Uh-huh.
right? 196.
Uh-huh.
This one you might be stuck at 2 for a very. This one will have like if you keep going through ones, it'll have 200 different layers.
Uh-huh.
Yeah.
Okay.
Okay, both are fine. I personally say this question fits more into the combination question because the order really doesn't matter,
Yeah.
right? Given a sequence of numbers, when you do the print, there's only one way to print them, increasing order. So that's a good way to do it. Okay. All right. Any other things I should go over? We have like, I'll stay for like 3 or 4 more minutes. Any other questions?
Could we just look at the solution for the ring buffer key reverse?
Okay.
Just kind of walk me through what that's doing exactly. It's
All right.
pretty
Ring
short
buffer
line of code.
reverse. All right. Is the question more about the syntax or about the?
It's kind of like conceptually, what are you doing? Like,
Okay.
To reverse that cue.
Where's the reverse?
Sorry, it was in the midterm, practice midterm 1. So it's the last question.
All right. Let's see.
So what is reverse buffer key? It just swaps.
Yeah, it just swaps the position, it just reverses the order of the cue.
Okay. So the idea is, wow, this is pretty tricky to be honest. Okay. Suppose you had, let's say this is head. 1, 2, 3, 4, 5. Right? If we wanted to reverse this, you essentially want to find these pairs of indices, right? Like, suppose we had a regular array. How would you reverse this array?
Swap the positions of 0 and the length minus 1.
Right, so you'd swap position 0 and position length minus 1.
Yeah, and then
Right.
swap position of 1, length minus 2, and 2, length minus 3. And if those are equal, don't do anything.
Yeah, so you just go from 0 all the way up to size divided by 2 and just swap like that. Right. In this example, it's harder to find where to swap because it's circular. So remember, we had the method last time, which lets us find where index 3 or index 5 was, if it was like still in the array, right? So index, if we wanted to find the third element, we would say 1, 2, 3, third element. Or 0, if we 0 index it, if we wanted to find the third element 0 index, it would be 1, 2, 3, 4, this one. The fourth element would be this one, right? And then we did that last time by using the mod.
Oh.
Right? We did the mod by the capacity.
That's what that's doing?
Yeah, that's what that's doing. And it's essentially trying to find where the 1 and the 5 is. The 1 is the head, and then the tail would be the size minus 1. So you can think about this array like this, but it's just shuffled around. This is index, think about this as index 0, 1, 2, 3, 4. It's trying to calculate where index 0 and index 4 are. Okay. Remember, because of our circular array, we're not starting from the beginning. We're saying this is our array looks like this.
So that's what the capacity stuff is doing?
Yeah, so that's what index 1 is front plus I mod capacity. So if I would be, suppose it starts at 0, then that would give you just front, right, which is here. And then what would index 2 give you? Front plus num used minus 1 minus I. Num used is 5, so index 2 plus index num used is 5, that gives you 7, minus 1 is 6, 6 minus I is 0, 6 mod capacity is 6 mod 6 is 0. So that gives you this one. Yeah.
Does this in any way handle the case when it's like you can't switch because there's an odd number? Does that work for that?
Yeah, so if you look at the very top, it says if int I is equal to 0, I less than num used divided by 2. Right? So if num used is odd, then it rounds down. Just like in this example, if num used is 5, 5 divided by 2 is 2.
Okay.
So you only swap this one and this one, but you ignore the middle one.
Right. So in this case, like when we reach the center, index 1 equals index 2, and those last 3 lines of code don't really do anything, but it still works fine, right?
You mean when you reach the middle?
Yeah, when you reach the middle. So like
Yeah. When you won't the for loop will never reach the middle because
Oh.
num used divided by 2
It's 2.
it rounds down. Like here,
yeah, probably.
5 divided by 2 is 2, right? So you'll only do I equals 0
Oh.
and I equals 1, but you won't get to I equals 2.
Oh, okay.
Okay? The idea is it's doing the same thing as this is, but it's just, instead of just putting the index directly, it's saying, okay, what is the index of the rotated one? Right? We wrote a method which lets us find where the head was and what the ith element is last time. And that was by that calculation over there, by the mod capacity. Okay? All right. Cool. Yeah, thank you. I'm out of time, but if you still have questions, feel free to ask me right now. Yeah, let's good luck on the exam. To SCPD students, good luck.